Welcome back, 8th graders. So now we're going to dig deeper into rational exponents and radicals. We're going to talk about what that rational exponent actually represents. I know we talked about it so that we could use fractions and our exponents in our previous sections, but now we're going to actually talk about and how to evaluate, or an easier way to evaluate rational exponents. So a rational exponent is a power with a fraction exponent. That's what makes it a rational exponent. So like a to the m over n. That's our rational exponent. Things to note: the denominator of this fraction is our root, and then the numerator of the fraction will stay the exponent. And you're like, what does that mean? Okay, so what that means is we draw our radical, right? What we have known up until now is just a square root. If our number is something other than 2, we're going to write it right here in that little check mark area. And then we're going to rewrite our base. And then if our exponent or our m value, our numerator, is anything other than 1, then we would put that number as our exponent. And so a to the m over n is the nth root of a to the nth power. That's what that represents. Or if you were to see the square root of, like say, 4, the 4th root of x to the 5th power, we can write it the reverse. So it goes both directions. So since we see the 4th root of the 5th power, my base is x, my numerator is 5, my denominator is 4. And so this would be numerator and denominator. I'll just make it denom. All right, so that's what a rational exponent is. This top one is how we can take a power and turn it into a radical. The bottom example is how we can take a radical and turn it into a power. That's how that works. All right, so how do we simplify roots? This is where I like to use those prime factorization trees that we've been doing in our warm-ups. So if we have, say, the square root of 20, we know it's not a perfect square. So what I do is I do the prime factor tree. So I know 20 is 4 times 5, and 4 is 2 times 2. And it's a square root, so I'm looking for pairs of 2. So in this case, here's a 2, and then the 5 still by itself. So this pair, only one of them like they get together in one car outside. I called this the house. These two go in one car outside, and the 5 is staying in to watch Netflix. But the square root of 20 simplifies to 2 square root 5. And if you're like, well, why? Well, because, and we can see it right here, 20 is equal to the square root of 4 times the square root of 5. And we know that the square root of 4 is 2. But instead of making you think of the perfect square that multiplies into a number, I think it's just easier to find numbers that multiply to the number we're going for. So sorry for the jump there. I needed to do some correcting. Say we're doing the cube root of 48. And so I'm going to go about finding numbers that multiply to 48. So I could go with 4 and 12. And 4 is 2 and 2, and 12 is 2 and 6. Now, 6, we still have to go, that's not prime. A lot of times what students struggle with is getting all the way down to their prime numbers. And so 6 isn't prime, so we're going to do 2 and 3. Now, I look at my root. My root is a 3 here, not a 2. So instead of doing groups of 2 like I did over here for the square, I'm going to find them in groups of 3. So here's 3 2s. They are getting together in a car to go out, I don't know, movies, something. And then in my cube root, we're left with the 2 times the 3 because they're left on their own in no pairs, or in no groups of 3. So now we simplify that and we get 2 to the cube root of, or 2 times the cube root of 6. And now we have simplified the cube root of 48 to 2 cube root 6. That, in my mind, is easier than having to search for either the perfect square or a perfect cube or a perfect fourth power or fifth power, etc. Because this time, if we do all the way down to the primes, we're just creating groups of whatever our root is. I'm going to pause this video here. In the next video, we're just going to go over examples of all of this using simplifying roots and changing things from exponent form to radical form and vice versa. So I will see you there, 8th grade.